Today is Wednesday, March the 8th. This is AP Chemistry. Today we're going to start talking about acids and bases, our final frontier. Okay? I know, I don't want it to turn into me. Okay? So, these notes are shared with you on Classroom now. Okay? We're going to kind of go through this. This is a very comprehensive set of notes. I strongly recommend that you print out these notes and have a hard copy. There are too many for me to copy for everybody individually. Okay? But I think that you should have those. There are some practice problems as we're going through on them and some examples that you could do in the notes and work out. So I strongly, again, recommend that you print these out so you can have them to take active notes on. It would probably cost you, it's probably like 16, 17 pages, isn't it? 22 pages.
Oh, I got it.
Okay? Now, there are some of those that you could maybe not do. Because I think there's some with how to use a calculator.
I'm printing off everything.
Okay? Now, okay. Y'all, you got to give me, hey, we got 25 minutes. You got to give me 25 minutes of focus now. Okay? We have just a few days, 2.5 weeks to try to cover this, and I really need 4. Okay? So, we're a week behind on where we needed to be coming into this. Okay? So, we've got to do the best we can to kind of cram it in, and because the more time it takes on acids and bases, the less time we have for review. And review is very, very, very important. Okay? So, we've already talked about acids and bases all year long. We've learned how to name acids. How do we recognize that something is an acid? Hydrogen is the front thing. How do we know something is a base? An OH. That really is this first definition, the Arrhenius definition of an acid and a base. An acid is anything, according to the Arrhenius definition, it's anything that increases the hydrogen, the H+, or the hydronium ion concentration. What's the hydronium ion?
H3O.
H3O+. The hydronium ion, if we look at water, water looks like this, but water is very polar. Okay? Did anybody go get the dukes? I asked somebody to go get them out of the microscope lab.
They're just in there sitting.
Okay? I just said somebody go get the dukes earlier. So, okay. So we have water. Hey, listen. Hey, Reese, if you want to be able to stay. Water is very polar, which means that the hydrogens are positive, the oxygen is very negative, which means there's going to be an attraction. So when we have something like HCl, where chlorine is stealing the electrons and making this very positive and very negative, the hydrogen is here saying, come on, chlorine, share the electron with me better. Come on, share with me. Chlorine saying, no. Okay, I'm bigger, I'm stronger, I can take the electrons if I want to. So water comes along and says, hey, hydrogen. How you doing? Okay? I got a pair of electrons you can share, you can have all to yourself. Okay? So the hydrogen says, hey, chlorine, I don't need you. And the hydrogen goes and attaches to that pair of electrons. So we end up having... We end up having the H plus because it leaves the electron behind, so we end up keeping the Cl minus with the extra electron, and then you get the hydronium ion. It's nothing more than a hydrated H plus ion. The H plus. When both electrons of the shared pair come from the same atom, we call that a coordinate covalent bond. Both electrons of the shared pair come from the same atom. H plus forms a lot of coordinate covalent bonds. Because it doesn't have any electrons, and therefore it'll share any pair of electrons it can come attached to. H plus will attach to ammonia. Ammonia looks like this. But when ammonia is in the presence of an acid like HCl, it will do the same thing. It will offer its electrons. It's highly electronegative, and so it's a very polar molecule. And so H plus can come and attach here as well, and we form our NH4 plus, the ammonium ion, forming that coordinate covalent bond as the H plus shares that pair of electrons. Okay? So the hydronium ion is nothing more than a hydrated H plus. Now, how many electrons does hydrogen have? One. So when it loses that one electron, what's left? Just the proton. Right? So an H plus ion is often called a proton, because that's all it is. So the next definition, the Bronsted-Lowry definition, just kind of broadens the definition. It's everything that's an Arrhenius acid is going to be a Bronsted acid. They do not contradict one another. It just expands the definition to everything that was a Bronsted-Lowry or everything that was an Arrhenius acid will now be a Bronsted-Lowry plus a few more. And in a Bronsted-Lowry, you don't necessarily have to have OH minus. Instead, anything that donates a hydrogen is an acid, an H plus, and a lot of times over it donates a proton, that's an H plus ion. Anything that accepts is a base. So in this case, ammonia accepted the hydrogen, no mention of it having an OH minus at all, but accepted the hydrogen, so they call it a base, because it's not H plus, a proton acceptor. Now, HCl loves to donate. It just broadens the definition. I'll give you some examples here in a second. And then our final definition, and put an asterisk by this one because this is no longer on the AP exam. So we're just going to look at the definition of it. We're not going to talk about it a lot, but it's very, 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 super very important in organic chemistry, which is the second year chemistry class. Organic chemistry does everything in terms of this Lewis definition. But in terms of regular chemistry or general chemistry, we don't use it as much. But Lewis, remember we talked about Lewis dot structure? Okay? Lewis said this thing for electrons. He liked to, deal with everything in terms of electrons. So rather than dealing with it being an H plus donor or an H plus acceptor, okay, he looked at it in terms of electrons. Which one is donating the electrons, which one's accepting. So when we're talking about this ammonia right here, instead of calling it a base because the H plus was accepted by the NH, it's saying, okay, well, the ammonia donated that pair of electrons. It donated, H plus accepted the pair of electrons. So it's just looking at it from a completely different perspective. The exact same reaction, just from the opposite end. So rather than looking at how the H plus is all about the electrons. Lewis is all about electrons. Now, an H plus is a great electron pair acceptor. Anything that has a lone pair of electrons can be an electron pair donor. Electron-rich things are Lewis bases. Electron-deficient things, positive things, are Lewis acids. Now, the only time that that's going to come into play or there'll be anything different is if we have kind of these strange reactions that we wouldn't normally think. And so it just, again, expands the definition. So if I looked at ammonia, and we talked about this one a little bit earlier, plus boron trichloride, BCl3. And what's unique about boron? It only has 3. Any group 3 metal only needs 3 pair of electrons around it. It doesn't have to have the full 8. It can be stable with 6 electrons. So in other words, it's got a space. It's got room at the end. So these two things can combine, and the boron can do that coordinate covalent bond with that pair of electrons right there. And we end up getting ammonia bonded to boron, chlorine, 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 hydrogen, hydrogen, hydrogen. We call this an adduct because they add it together. Okay? But Lewis would call this an acid-base reaction. Now, there's no H+, there's no hydronium ions, there's no hydroxide ions, there's nothing that would make us think that this would be an acid-base reaction in any way, shape, or form. But because this donated a pair of electrons, this accepted a pair of electrons, according to the Lewis definition, this is an acid-base reaction. So this is the base because it donated the pair. This is the acid because it accepted the pair of electrons. Okay? It's all perspective. We can look at the reaction of HCl plus water, H2O, and that's going to make H3O plus Cl minus. And in terms of electrons, we have chlorine bonded to hydrogen plus the water. So that goes then to plus the Cl minus. Okay? So when we're looking at this here, from the Arrhenius definition, this is an acid because it produced H3O plus. Anything that produces H3O plus, that's an acid. Okay? In terms of the Bronsted-Lowry, it's an acid because it donated a hydrogen to the water. But now, what makes Bronsted-Lowry broader is that water is classified as a base. In Arrhenius, water is just the medium. Water is nothing. But according to Bronsted-Lowry, water is acting like a base because it's accepting the hydrogen. In the Lewis definition, you're going to look at the exact same reaction, but the H plus is going to be considered, this is an acid because the H plus is accepting the pair of electrons. The water is the base because it's donating the pair of electrons. It's all perspective. It's just kind of like how a chicken, a hen, and a pig might look at a bacon and eggs breakfast. Okay? The hen can be totally dedicated to laying the perfect egg. Everything just right. Complete dedication. But the pig has to be committed. Okay? If he's going to produce the best bacon, it's going to cost him a whole lot more than the hen. Okay? They're going to look at that breakfast from a different perspective. Okay? They're going to look at the same eggs and bacon, but they're going to see it in a completely different light in a different way. Lewis and Bronsted and Arrhenius looked at the exact same reactions and just looked at a different way. Now, we call it a Bronsted-Lowry definition because, once again, two guys completely separate, but at the same time came up with the same definition. So they both get credit for it. Yes, sir?
Well, on like the test, what would be like, according to the Lewis definition, what is this? Like,
yeah, and again, the only time that's going to be a challenge is when you have something that doesn't have hydrogen and oxygen in it. Okay? Because this HCl is going to be an acid, no matter whose definition. Yeah, that's because I did underhand.
That's why you retired the coach.
That's right. That's why they put me on the bench. Get follow your shot, get your rebound. Okay.
I don't need to, so I did.
Okay. So, as I was going to say before my pen ran out, HCl is going to be an acid by anybody's definition. HCl is going to be an acid. Now, there's no way that HCl will be an acid in one definition and a base in another. If it's an acid in one, it's going to be an acid in the other. It's just, I don't know, I remember when I was learning this, quote, new math, which was now very old math for y'all. They probably have changed it again, but we used to talk about subsets. Okay? Here's the Arrhenius definition. But then you go to the Bronsted-Lowry definition, which is going to encompass everything that's in Arrhenius definition plus a few more. Okay? And then you go to your Lewis definition that's going to encompass all of your Bronsted-Lowry and Arrhenius and just expanded the definition just a little bit more. And this is just to fill in these rare cases that don't have any hydrogens and oxygens. Now, for us, the Arrhenius definition is really the one that we're going to use the most. Because it's the one that pH is all based upon. It's going to produce the H plus and the OH minus, and we're going to be worried about that. We may have to look at the Bronsted-Lowry. It's pretty easy. Okay? Now, in the Bronsted-Lowry, we have this thing called conjugate acids and bases. And I think you guys all did this in Chemistry 1.
Oh, I said I won't.
Okay? Now, when we look at nitric acid, what we want to do is we want to, well, how did the nitric acid change to go from here to here? In the Bronsted definition, notice that this is donating a hydrogen, okay? That's supposed to be water. That's supposed to be an H2O right there, okay? So it donates the hydrogen to the water and makes H3O+. And then the nitrate is left by itself, okay? So, by the Arrhenius definition, HNO3 is an acid because it produces H3O+, the hydronium. Anything that produces H3O+ is an Arrhenius acid. That's our normal definition. Okay, anything that produces a hydroxide is a base. That's what we've been talking all year long. Okay? But now, if this is in equilibrium, if we can make it go back this way, now the H3O+ to go from here to the water, how does it change? Loses a hydrogen. So it's an acid, but to differentiate, it's the conjugate acid. Where have you heard the term conjugate? Spanish, right? Estoy, estás, está, estamos, están. Okay? Estáis. Okay? Okay? Hey, they're different forms, listen, different forms of the same verb. If they're conjugate, they're related. Okay? Conjugates are related to one another. When you conjugate the verb, it's all the different forms of the same verb. So the conjugate acid is related to the other side. They're related to each other. The base and the conjugate acid, that the base then accepts a hydrogen. It now has a hydrogen it can donate. So a base forms a conjugate acid, and acid forms a conjugate base, because now once the acid donates a hydrogen, now it has the room to accept one back. Now in terms of strength, what makes an acid strong? When we say a strong acid versus a weak acid, it dissociates at 100%, right? So when we look up there again, we've memorized our 6 strong acids. Okay? We've memorized our 6 strong acids because those are the ones that ionize 100%. So our Ka, our equilibrium, our acid equilibrium constant, Ka, says very large. Remember, K is the relationship of products over reactants. If we have 100% dissociation, that means you have all products, reactants are approaching 0. So when you divide by 0, your calculator blows up. Isn't that what Mr. Sandlin says? Something blows up, according to Sandlin. But you approach, as the denominator is approaching 0, the answer is approaching infinity. Okay? So Ka, we can just put very large, meaning that it's all to the right, 100% ionized, 100% broken apart. Okay? So what does that mean if HNO3 is one of our 6 strong acids? That means is when you put it into water, it's going to go 100% this way. What does that mean about nitrate's attraction for the hydrogen? If it's got 100% of these, it's going to break apart into H3O plus and NO3 minus. It's very weak, thank you. If 100% of them break apart, that means they don't like each other very much. Right? They're together because they're kind of forced to be, but the minute they have a chance to get apart, they do. Okay? Now, so listen, let's take this then the other direction. So then the NO3 minus, the thing that just broke up with the hydrogen so readily and easily, what does that mean about its attraction for the hydrogen to go back to HNO3? It's very, very weak. Okay? A base, the strength of a base is, well, what attraction does it have for an H+? The greater attraction it has for an H+, the stronger the base. So, therefore, a strong acid is going to make a weak conjugate base. Because if it breaks up readily as an acid, that means it's not going to have an attraction for the hydrogen back. The stronger the acid, the weaker the conjugate base is going to be. So if we look here at NH4+, NH4+ is a relatively weak acid. I'm trying to see if it's up there on the chart. Yes, it's right. It's the second column right in the middle. NH4+ going to H+ and NH3. Okay? 5.7 times 10 to the minus 10. That's a pretty small number. Does that mean it's reactant favored or product favored? Very reactant favored. Okay? Because products over reactants is a very small number. So that means reactants is big and products is small. So therefore, if this is a very weak acid, which means that it likes holding on to the hydrogen, it doesn't want to get rid of that hydrogen. The ammonia has a very strong attraction for that hydrogen. So when it does give it back, what does that mean then about this base? It's strong. So this reaction is going to lie way over here on the left side. Okay? So the weaker the acid, the stronger the base. Acids make conjugate bases, bases make conjugate acids, strong makes weak. So in terms of Bronsted, it's kind of opposites. Now Bronsted-Lowry is the only definition that has these conjugates in it. You don't have conjugates with Arrhenius, you don't have conjugates when you're looking at it from Lewis, but when you're looking at it from Bronsted-Lowry, you get these conjugate acids and bases. So let's finish today and just kind of look at some examples of that. I think there's some in here.
I can't wait. Good exercise.
Yeah, I can't lift it up any higher because the answer's on there.
You try.
Okay? So, if we have HBr plus NH3,
Where's my pencil?
HBr plus NH3 goes to NH4 plus Br minus. Okay? So I want to label the acid, the base, the conjugate acid, the conjugate base. So in terms of Bronsted, an acid is a proton donor.
Bless you.
So which one is my acid, which one's my base? Okay? And again, we can say, well, this has the hydrogen, this is going to be my acid. Okay?
So we can do that?
Yeah, I mean, the definitions do not contradict one another. So you just have to look at it from that perspective, though. So now, how is this one changing to go from here to there?
Losing an H.
Losing an H. So therefore, this one, these are the two that are related to one another, right?
Yeah.
So they're the conjugates. So this is the acid, so what's that make this? The conjugate base. And these are in equilibrium, so the reaction goes both ways. So the Br, if you look, Br minus to come back to here, what's it doing with hydrogens? It's gaining, so it's acting like a base. Okay? Now, HBr, what type of acid is that? It's one of our 6 strong acids that we've memorized. Okay? I keep speaking that as if it were, you know? Okay? So HBr is a strong acid. What does that mean about this in terms of a base? It's weak. Okay? Now, this then is my base. This is my conjugate acid. Okay? We call this a conjugate acid base pair. This is a conjugate acid base pair.
So it's just the addition and or subtraction of the H?
Yes. So when we look at this next question down here that says, what is the conjugate base of H2S? What type of substance makes a conjugate base? An acid. So if we want the conjugate base of H2S, that means H2S is acting like an acid. So what's left after H2S donates a hydrogen? HS minus 1. Because now, so the conjugate base of this is going to be HS minus 1. So what is the conjugate acid of NO3 minus? Well, conjugate acid, what type of substance makes a conjugate acid? A base. What do bases do with hydrogens? Accepted. So what species remains after this accepts a hydrogen. HNO3. Okay? So the conjugate is the species that remains after an acid donates a hydrogen or after a base accepts a hydrogen. Okay? So, tomorrow we'll look at the pH scale.
Oh, that's my
Okay?
scale.
Do pH for strong acids and bases.